Okay, in this video we're looking at Unit 9A and the concept of functions, which are the building blocks of mathematical models. Now mathematical models, or just models in general, are something that are used very frequently. So an example here that we have from the text is if you're building an office complex, the real office complex may not look exactly like what you see in what we call a scale model used to design it, but the model helps the architects create the design, and also things that may surround the design. If you're building a model of a huge office complex that may be like 35 stories high, you can get what's called a scale model. You build it on the computer, and then from there you tweak things on the model, so you don't have to be guessing as you're building the real thing. Another model is like a roadmap. Roadmap doesn't always look like the real landscape, but it serves as a model of the road system. It can be extremely useful when you travel. The GPS and those type of things, those are models of what you will actually see. So in this case, we're really looking at beginning concepts of the idea and purpose of mathematical models. So mathematical models, they're similar to these architectural models or roadmaps, and what they do is they help us represent something real, and it helps us understand that real thing. So now, to be a little bit more specific about mathematical models, these things are based on relationships between quantities that can change. So for example, one thing, there's a relationship between the wind speed and stress on a bridge. If you increase the wind speed, it's going to put more stress and strain on that bridge. Or, there's a relationship between worker productivity and unemployment. If you don't produce anything at work, you're probably not going to be employed. If you are producing at high levels and effective levels, there's a high likelihood that you'll be employed, etc. And these relationships that we use a mathematical tool called functions, and we've been looking at this idea of functions all semester long. Functions are just building blocks of mathematical models, and they can be represented with a formula, they can be represented with a graph, and sometimes there's only a single function. Sometimes there are many functions. So, as scientists are studying the Earth's climate, there are thousands of functions that actually require supercomputers for the analysis, but the basic idea of these functions is all the same. Okay, now like I said, we've already used functions several times in this book without calling them, the function by name, and I may have thrown that word out there several times. But for example, when we looked in Chapter 4, we looked at the balance in a savings account as it is related to interest rate and monthly deposits. Okay, that was a function. Chapter 8, we saw how population is related to growth rate and time. That's another function. And these relationships are called functions because they specifically tell us how quantities vary with respect to one another. And so now we're going to look at some of the language and notation used in functions. So first thing when we're dealing with functions is what's called a dependent and independent variables. And we'll look at an example here. So suppose that we wanted to model the variation in temperature over the course of the day. So a couple of variables here. We have temperature, and then we're looking over a time of day. So we can see the model down in table 9.1. So when you're looking at functions, the first thing is to recognize that we have two quantities that are involved. One is time, one is temperature. So our goal would be to express the relationship between time and temperature in the form of a function. So the quantities related by a function are called variables because they change or vary. In this case, temperature is what we call the dependent variable because it depends on the time of day. If you're early in the morning, temperature is likely to be lower. If you're in midday, it's likely to be higher. So the temperature is dependent upon the time. So time is what we call the independent variable. Because independent of temperature, time is always moving forward. The temperature doesn't affect the time, but the time can be an effect on, depending on what time we look at, the temperature may be different. So we say temperature varies with respect to time. And another key thing here is notice that there's exactly one value of temperature for each time of day. That's a big idea of the function, is every time you look at one value of your independent variable, there should only be one value of your dependent variable. So at 6 a.m. it's 50 degrees. Because if you looked at 6 a.m. and it said it's 50 degrees and it's 70 degrees, that wouldn't make sense. If you're in the same city and thermostat's showing two different temperatures, you'd be like, what is going on here? That's not a function. So a function for every when we look at an independent variable, every one moment in time, in this example of our independent variable, should only produce one temperature. Now the temperatures can be the same at different times in the day, that's okay, but one time can't shoot out two different temperatures. So now we look at this idea of writing functions. And I know this is a lot of English here. This section will be quite a bit of English. But when we're writing functions, we often write related variables in the form of ordered pairs with the independent variable first. So the independent variable, a lot of times people think of it as the x value, and the dependent variable will come second. So in this case, when we look at time, so the independent variable and then the dependent variable. So that's going to always be our order. And we use special notation or representation for functions. So you might use x to represent, again, the independent variable, and that's pretty commonly used. Y to represent the dependent variable. So we'd say something like y equals f of x, and this just means, or is read as, y is a function of x, which means that y is related to x by this function f. So in our case here, we have time and temperature from the example that we looked at in table 1. And so sometimes you can change out these variables, your independent variables and dependent variables, to help better represent your relationship that you're looking at. So we could say lowercase t represents time, capital T represents temperature. So we could say that temperature equals f of little t. So every time we say capital T, that's temperature, lowercase t, that's time. And again, this indicates that temperature varies with respect to time, or that temperature is a function of time. And remember, the dependent variable is always a function of the independent variable. In this book, your book illustrates functions as kind of like a box. Sometimes people use machines, where you take an independent variable and you run it through this box, and it puts out a dependent variable. So if you input a time like 6 a.m., it outputs a temperature of 50 degrees. One of my favorite examples of a function is like a vending machine. Okay, the vending machine, if you were to imagine inputting into a vending machine, this would be, you would input a code and then your output. So you'd input a code if this was a vending machine, and your output would be whatever goodies are in that code. So if you hit like A4, and that's where the Reese's are, okay, then A4 is going to correlate to Reese's, so that input of A4 has an output of a Reese's. And again, the key idea there being that when you type in a code or one input, you should get exactly one output. Like if you type in B7, that should only give you whatever's in the B7 slot. You shouldn't hit B7 and have like 8 things drop down out of the vending machine. Although, as a consumer, we love that, but if you own the vending machine, you wouldn't be too excited. So we'd say it's not functioning properly. So that's one relationship that I like to use when I'm describing a function. Okay, so here's your formal definition of functions. Just describes how dependent variables change with respect to one or more independent variables. And you'll see like f of x, and that's how that is read. Now, functions describe, there's a lot of functions that describe changes with respect to time, you know, the weight of a child or consumer price index. Those both vary with respect to time, but not all functions involve time. You know, we looked at mortgage payments. They were a function of, in some cases, the interest rate for the mortgage, because the amount depended upon that interest rate. So we'd say that mortgage rate or mortgage payment was a function of interest rate. Similarly, you could look at gas mileage in a car is a function of the car's speed. Because the mileage is different based upon different speeds. So depending on how fast you're going, your gas mileage may be good, may be bad. But again, that's something we could use a mathematical model to get a relationship or show a relationship between the two. So it's not always, we're not always dealing with time. Now you're going to hear some terms such as domain and range. Okay, the domain is just a nice name. When you're looking at a function, it's the set of all the independent variables, or all the values that the independent variable can take on. And a lot of times, domain, when you're looking at a function, will be on the horizontal or the x-axis. So if we're thinking back to our vending machine question, the domain would be the set of all possible codes to put into a vending machine. The range are all the values of the dependent variable that correspond with the domain. And those are usually, when you're looking at a graph, those are usually on your y-axis. And if you're again thinking of the vending machine, the range would be all of the different goodies that are inside that correspond to codes. And so that's your difference between a domain and range. Domain, always your independent or your inputs. Range, your dependent or your outputs. So let's look at a couple of examples here. Again, there will be a lot of English in this, but hopefully you don't mind some English in here. Whoops, sorry about that. So in this one, it says, in each of the following situations, state whether two variables are related in a way that might be described by a function. If so, identify the independent and dependent variable. So you jump from an airplane with a parachute. I love how they just throw that in quotations there, you know, with a parachute. You want to know how far you've traveled at various times during your descent. So the two variables that I see here are going to be time as one, and then the other one is going to be, how much distance you have fallen. Those are the two variables I've seen. We can definitely relate those two, because at any given time that you're in the air, you can select a time, and then you can correlate that to a distance that you have fallen. So in this case, we will say that time is going to be your independent variable, and the distance fallen is going to be your dependent variable. And whenever you're dealing with time, time is always independent. Time cannot be affected by other things, at least in the reference of what we know in Math 1030. You get into physics, you might be able to make some arguments there, but time is always independent.